So far what we have done is we have looked at molecular origin of van der Waals interaction. We did a little bit of basics looking at dipole, induced dipole, and then we talked about following that I showed you a table where we had listed several molecules or atoms and we were looking at molecular interactions and what is the contribution of the Debye interaction, the Keesum interaction and London dispersion forces to the overall van der Waals interaction. Okay, that is what we had done. So, what we will try and do today is these two topics. One is looking at van der Waals interaction between particles now, and we will look at a very simple and nice concept called scaling of van der Waals interaction for macroscopic objects. What I mean by that is if you so macroscopic objects essentially corresponds to particles, right, or any colloidal length scale species, right. Okay, so just to do a quick recap, so this is what we had done in the last lecture. So if I have two atoms or molecules which are separated by a distance x, we said that the total contribution to the van der Waals forces or van der Waals interaction comes by the Debye interaction, Keesum interaction and London dispersion forces, and this is what we wrote if we have two dissimilar atoms or molecules 1 and 2, and that kind of simplifies to this equation if we have interaction between two similar atoms, and we said that all this constant here, that is your beta, right, that is what we had done. And I had also mentioned that this is analogous to the attractive term in the Lennard Jones potential, right, that is what we had done. Okay, now so if you want to calculate the van der Waals interaction between colloidal particles, we can actually extend. So here we were assuming that there are two atoms or two molecules which are interacting. Now you can consider a colloidal particle 1 and a colloidal particle 2 as consisting of collection of large number of atoms and molecules, right. In fact, we can calculate that, right, if I know what is the size of the particle that I am dealing with, and if I know the chemistry of the particle, if it is gold, silica or anything, right. I mean I should be able to calculate the number of atoms or molecules that constitute the colloidal particle that we are considering, right. Now the interaction between colloidal particles are essentially summation of the pairwise interaction of the constituent atoms or molecules that make up the particle. Okay. That means, okay, in this case I am considering a case where I have 16 a particle which is made up of 16 atoms. Okay. Similarly, there is another particle which is again made up of similar number of atoms, right. I take one particle and I look at its interaction with all of them, okay, all the 16, right. Then I go to the next one, okay, and again I look at the interaction with all the other 16 atoms or molecules and I sum them up. Okay. So this pairwise addition of the interaction of every atom or the molecule that constitute a particle with the atoms and the molecules in the other particle is what gives rise to the total van der Waals force of interaction between colloidal particles. Okay. So that is again just like atoms and molecules, the van der Waals force of interaction or van der Waals interaction between colloidal particles are again they have their origin in the dipole and the induced dipole interaction, just like the atoms and the molecules. But one thing to keep in mind when you compare the interaction between molecules and particles is that the strength of van der Waals attraction, okay, in the case of macroscopic objects, that is colloidal particles, okay, are much larger because each particle has a large number of atoms and molecules. That means, if I were to calculate the strength of van der Waals interaction between atoms and molecules and compare that to the strength of van der Waals interaction between two macroscopic particles, okay, at a particular separation distance, you will see that the strength of van der Waals interaction for the macroscopic particles is larger compared to that for the molecules and the atoms at the same separation distance. Okay. So, the other thing to notice is that they are relatively long ranged compared to the atomic or molecular forces, okay, and they can have interval of influence ranging from about 0.2 nanometer to 10 nanometer. Okay. Everybody understand the statement? Okay, let us go back. Okay. I just want to make a point that they are long ranged compared to the atomic or molecular forces. Okay. For that I will again go back to this picture. Okay. Lennard-Jones potential, okay. You look at both the repulsive part and the attractive part, okay. And if I were to write what is the range of interaction, I can say it is up to about 0.8 nanometer, right. Beyond that distance, you do not have to worry about the both the terms are essentially 0. That means you do not have to worry about these interactions beyond that distance. Okay. But however, if you take van der Waals forces between colloidal particles, they have a range going from about 0.2 nanometer to 10 nanometer, compared to 0.8 nanometer, they are more long ranged, right. That is the point that I wanted to make. Now, we will do a very simple exercise, which is what is called as scaling of van der Waals interaction between large bodies or large particles. Okay. Good thing about this exercise is that it will also help you to think about how do people calculate van der Waals force of interaction between the particles, okay, or the macroscopic particles. So, what you have is case A and case B, okay, that is there is a subscript A that corresponds to case A and there is a subscript B that corresponds to case B. So, R is the radius of the particle and they are separated by a distance R A in the first case and R B in the second case. Okay. And in the case both for case 1 and case 2 or case A and case B, the particles are of equal size, okay, and we are saying that they are spheres of equal size and they are separated by some distance. Okay. We will assume that the spherical particles are of same composition. Okay. That means, if I were to think about case A, if I have taken say silica particles, okay, the other particle will also be silica particle, and then similarly all the particles will have the same composition. Okay. That is done just to keep things simple. Okay. You can do a similar kind of exercise also for the cases where the composition need not be same, but for simplicity we have done that. Okay. So, these two individual cases, case A and case B, are in a way related because the radius of spheres in A and B are related by this R B is equal to F times R A. Okay. That means, if because if F is greater than 1, the size of R B is greater than the size of the particles that you see in this R A by a factor F. Okay. Similarly, the distance of separation between the spheres in A and B are again related by a similar kind of way, where R B is again F times R A. Okay. So, we will ask a question as to what can we say about the van der Waals force of interaction in the case A and what is the van der Waals force of interaction in the case B. Okay. That is a exercise that we will try and do. Okay. So, we will take configuration A that is given here. Okay. Now, if I consider one atom in A and one atom in one atom in particle 1 and one atom in the particle 2, okay, we know that there is a attractive van der Waals force of interaction. Okay, that means every atom in sphere 1 attracts every atom in sphere 2 with an attractive potential or energy which is given by phi A is equal to minus beta 1 1 x power minus 6. Okay. So, we know where that comes from. Okay. Now, because we want to calculate the total interaction, okay, before that what we have to do is we should calculate the number of atoms in particle 1 or sphere 1 and the number of atoms in particle 2 or sphere 2, right. If you define N A as the total number of atoms, okay, if you define N A is the total number of atoms in the particle, the number of atoms per unit volume is N A divided by volume. I can relate volume to the density and the mass. Therefore, the number of atoms per unit volume, okay, is given by rho N A divided by m. Is it okay? Right. N A is the number of total number of atoms divided by the volume of the particle will give you the number per unit volume, right, number of atoms per unit volume, right, and that number is going to be same for both the particles, right. In fact, whether I take, because these are made up of same composition, they are same composition, whether I take N A into rho divided by m, that is the number of atoms per unit volume, whether I take particle 1 here, particle 2 here, particle 1 here, particle 2 here, that number is going to be exactly same, right, because their composition is same. Okay. Now, if you take some differential volume element, okay, d V is a differential volume element in sphere 1 in configuration A. Okay. This d V 1 A corresponds to a differential volume d V in sphere 1 in case A, right, that is your case A. Similarly, if d V 2 A is the differential volume that you have considered in sphere 2, okay, and again corresponding to case A, then this term and this term will give you the total number of atoms, right. It will give you the total number of atoms that you have in the differential volumes d V 1 A and d V 2 A. Is that okay?
Sir,
yeah.
N is the total number of atoms,
Yeah.
But the cases are different, no? So you are considering both have the same number of atoms in both the cases.
It's the same. You see, if I take a colloidal particle, right? I'm saying that I have a colloidal particle. Okay, if it's a chemically homogeneous, okay, if it's say gold nanoparticle for example, whether I take a very small fraction of the particle and I calculate what is the number per unit volume by considering this, or I take another small volume and I calculate, or I calculate it for the entire particle itself, it will be the same number, right. So, therefore, this rho N A by m, that is what I was trying to say, right, whether I take case A or case B, okay, or any particle, this number is going to be same because they are of same composition. Okay. The total number of pairwise interactions are essentially the product of the total number of atoms that we have in the differential volume d1a and in the differential volume dv2a. Okay, that is the total number of pairwise interactions. Okay, one of the way to think about this would be that imagine that I have two particles. Okay, there is a colloidal particle, just for the sake of simplicity, there is a colloidal particle which has only two atoms. Okay, so the number of pairwise interactions are interaction of this with this and this with this, that makes it 2. Okay, and the interaction of this with this and this with this, that makes it another 2. Okay, therefore, the total number of pairwise interactions are 4. Therefore, the number of atoms in this multiplied by the number of atoms in this will give you the total number of pairwise interaction that you should consider, right. That is this.
So here Na is the total number of atoms in a particle one.
Yeah.
In part.
So yeah, I mean, okay. So Na is defined as the total number of atoms. Okay. Now, okay. So do you guys have a confusion that why is this rho Na by m same for both the cases? Is that your confusion? I mean, okay. Let me put it this way. Okay. So say that I have gold nanoparticles, okay, and say that they are prepared, say that I have made particles of different dimensions, okay, by a same technique. For example, I have used identical reaction to make these particles, but I have a way of tuning the size. Okay, maybe we define this aspect ratio, right. This is L divided by D is the aspect ratio, and aspect ratio is different in the 3 cases. Now, if the reaction chemistry that is involved in the preparation of all of these are the same, then I would expect particles of same chemistry, right, same composition, right. Now, if the particles are of same composition, whether I take this particle or this particle, calculate the number of atoms per unit volume, okay, will be same for all of them, right. So, all I am trying to do is define a quantity called number of atoms per unit volume. Okay. Let us not say that, you can say that Na is the number of atoms, right, okay, in a given volume, right. Therefore, you can define number of atoms per unit volume, that will be this quantity, and because the compositions are the same, this is going to be same for all the particles that we have considered. Is that okay? Therefore, the total number of pairwise interactions, okay, between the volume elements that we have considered, okay, is this. So, now instead of considering individual atoms or molecules, if I have taken a differential volume now, okay, dV1a and dV2a, right, then I can think about what is called as the increment in the, so they were interacting by some energy earlier. Now, because I am considering a large number of atoms, right, in each of these differential volumes, then the increment in the interaction is given by, this is this term that we had for interaction per pair, right. So, let us go back, right, this, okay, is the interaction per pair, right, multiplied by the number of pairs, okay, the number of pairs multiplied by the interaction per pair, okay, will give you the increment in the interaction potential. If I want, I can integrate that, okay, over the entire volume of the spheres, then I would get the total van der Waals force of attraction between every atom between the two particles now, right, because I have considered all the atoms now. There is going to be a double integral, right, is going to be a volume integral, right. Okay, so I just have to integrate this, okay, because this is constant, I have taken it out. Beta is also constant because once the material that you are considering is fixed, beta is fixed. Therefore, double integral of R A power minus 6, because R A is the separation distance here, right, that is a separation distance now multiplied by the two differential volumes, right. So, that is the total interaction potential between all the atoms in particle 1 which has a radius R A and the particle 2 which also has radius R, and they are separated by a distance R A, right. I can do a similar exercise. Okay, yeah.
They are not related, right? Volume and
what is it?
they are not related, right?
What do you mean?
Volume.
Which are not related?
V1A, V2A, and
Yeah, I mean I could have in fact you don't have to go through this concept of differential volumes.
this
Okay,
all it is.
you can also take the entire sphere and I can do it. Okay, then it will be a much simpler exercise as well. Okay, you can do that as well. Yeah. Now I can do a similar exercise, okay, and I can calculate the van der Waals force of interaction for the case 2, right. For the case 2 we had again sphere 1 and sphere 2, they are separated by a distance R B, right, and of course their radius were also R B, right. And if I do that I will get a similar expression. Okay, only thing is instead of R A I would have R B to the power of minus 6, and you will have differential volume 1 in the case B, this is case B, right, and the differential volume 2 in the case B. Now, we know that R A and R B are related, right. R B is larger than R A by a factor f, okay, and because the volume goes as r to the power of 3, okay, I can relate the volume differential volume in the case of B to the differential volume in the case of A, okay, as dV1B is f cube times dV1A, right. Similarly, I can say dV2B, that is the volume of the differential volume V2 that I have considered in the case B is a factor f cube times differential volume in A, right. If I put them back into this expression, so I have f R A power minus 6, there is F3, F3, okay, this essentially gets cancelled. What you end up with is whatever that you had for phi A. Therefore, this tells you that the van der Waals force of interaction in the case B is same as the van der Waals force of attraction in the case A. Okay. So, the implications of this is that if I take like say 100 nanometer particles, okay, and if I am talking about the van der Waals force of interaction between them like say at 10 nanometer, okay, or I take 10 nanometer particle and I am asking a question as to what is the van der Waals force of interaction at a separation distance 1 nanometer, right. So, 100 divided by 10 is the scaling of the size, okay, that is by a factor of 10. Let us look at the scaling of the distance, 10 divided by 1, again there is a factor of 10. In cases like this, the 100 nanometer particles at a separation distance of 10 nanometer will experience the same van der Waals force of attraction as the case where you have 10 nanometer particles separated by a distance of 1 nanometer. Okay. So, that is the implication of this result. Okay. Yeah, so that is all I wanted to say today, and then what we will do is, so yeah, so this is again I have kind of a similar thing that I mentioned, right. If you take 0.3, yeah, basically the same concept that I mentioned, right.
But there is a
Yeah.
scaling, so it seems like there is a scaling. No?
Yeah. Yeah, that is why, right. I mean, we were saying the scaling of van der Waals interaction, right. That is what you know. So, that means if I take two cases where both the dimensions of the particles and the separation distance scale in the same way, okay, in two cases, in such cases the van der Waals force of attraction in the two cases will be identical. Okay, that is the crux of the result.